So when we're looking at motion, we are going to basically be using a bunch of tools to try and translate the motion. And one of those tools is, I know, everyone's favorite friend. It's Mr. Graph. I know, people love graphs. It's like they cannot get enough of graphs. Or they really hate it. It usually goes one of two ways. But in physics, we just can't get enough of graphs. So I hope you get over your possible disliking of graphs, because we're going to be using them a lot because they have tons of information in them. All right. Now, one of the other tools that we've also discussed is the motion map. Now, the cool thing is a motion map can be made into a graph. And so if you looked at the motion map, you said, you know, I like that because it allows me to visually see what's going on, but this graph thing, not working for me. Then you can translate one into the other. Same thing. If you're looking at a graph and you're saying, I love the graph, it just makes sense to me, which in all honesty is me personally. But then you're like, this motion map thing I find confusing and it's complicated and things like that. You can then create a motion map from that graph. Or if neither of those things are working for you and you're just not sure if you're doing it right, you could technically create both a motion map and a graph independently and then compare them to see if you are doing one or the other incorrectly. Or if you're doing it, if they both match up, you're probably doing you're analyzing the situation correctly. So very powerful tools. So what I'm going to show you how to use a motion map to create a graph. So first thing I've done is I've just done a basic motion map. This is an object traveling at a nice constant velocity, and I want to make a graph from that. Well, if I look at this, in all honesty, my brain says, well, they covered the same distance in each unit of time, because that's time 1. Oops, let's make that 0. Time 1, done and done, and then time 2, so forth, because they're always the same spacing and time intervals. So I covered the same distance, same amount of time. All those arrows look the same length. Those arrows represent the velocity, because not only does the size of the arrow tell me the speed, but the direction tells me direction. So speed plus direction is velocity. And that's way more powerful than just speed. So now I'm going to actually create a graph from this. So in order to do that, it's kind of simple, actually. I'm going to take a few steps. So one, I'm going to flip this 90 degrees. Okay, so if I flip this 90 degrees, then I'm basically going to just rotate this 90 degrees. And so what that leaves me with, and I can do this because that's position. This line here represents position. And on a position time graph, position is vertical, and then time spreads this out onto the graph. All right, so if you flip this 90 degrees, here's my position time graph. So I'm just going to redraw this. So I have a dot here, a dot here, a dot here, and a dot here. Okay. So if you twist your head sideways, or maybe move if you want to flip your screen so you can see that this and this are actually the same thing, then all we're going to do is this is time 0. So here's this is my time element of my position time graph. So that's 0. This would be 1, 2, 3, 4 seconds. All right, and these would be the corresponding positions, but I'm not too worried about that number here. So what I'm going to do is I'm going to draw this onto this graph. So at time 0, I am at a position of 0, because this is my position 0. They line up. So I'll put a nice big dot there. Then at time 1, I'm at this other position. So I drew that in, okay? But this is time 1. So I'm going to stretch that out so that it's at the intersection of time 1. So I'm kind of pulling it onto the graph using time. So then this is time 2. So let's see where that intersects with time 2. So that'll cause this intersection here. And then time 3 will intersect with this guy. All right, and I'm left with this. So we can see where those intersect. And then, let's just pick a new color here, why not? And then we can draw a nice line that connects all these, and we can see that we have the graphical representation of a position time graph. So this right here is an object traveling at constant velocity, and this right here we also have constant velocity. And we know this because we only have one slope on a position time graph. Okay, and here we can visually see we have constant velocity because each of these velocities are the same. Okay, all of our arrows are the same length with the same direction, so we have constant velocity. So you can do the same thing. All right, you can translate a motion map into a graph. If you really want, you could say, well, here's my graph, and then I'm just going to grab these points and I'm going to put them over to here, and then, turn your paper sideways. Congratulations, you've just created a motion map from your graph. All right. Now this also works, so I'm going to draw it again. I'll do another one. All right. Same concept works if you are speeding up. All right. So let's just say we're speeding up here. So let's go to a new color. Yes, I agree. Let's go with this pretty blue. All right. So now if we were to draw a motion map of an object that's speeding up, we would start at rest, and then we're going to go faster. We're going to cover a little ground, then more ground, then tons of ground. Okay, so if I draw my arrows, doot, 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 and obviously I can go even farther. So, we'll say it's really long. All right, so these is time 0, time 1, time 2, and then this is a position of 0 right there. You got to make those markings just so everything's clear. We'll go T3 on that one. So now again, I'm going to flip that 90 degrees. And so now I have my position, part of the position time graph. And then I just draw time, and time stretches out. And so if I redraw this, I draw a little smaller, but I basically have doot, 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 and then doot. Something like that. Okay, so I've got increasing spacing as time goes on. So now at time 0, I was at position 0, so I'll put a nice dot there. At time 1, time 2, time 3. So at time 1, I'm now going to intersect. I'm going to end up over here. Time 2, I'm now going to end up over here, because that's where it intersects. And then time 3, I'm going to end up over here. And we can see that we no longer have a straight line, but we have a curve going on. And in all honesty, for conceptual purposes, if you just want to play connect the dots, it's like, oh, look, it's a curve. All right. So we can see that here we have acceleration. All right. And we have this because we have multiple / changing slopes on the position time graph. Okay, so this works for constant speeds. It could even work for erratic speeds. If you wanted to do one of the examples that we had before, where the object is actually turning around, I can do that too. Sure, we'll do a quick one, the object turning around. So let's go back. Purple. So let's just say the object moves forward at a constant speed, and then stops, and then turns around. This is the exact one that I had before. All right, so again, this is the position of 0, time 0, time 2, time 3. I should do some arrows here. And as you can see, it's really okay if you draw the line above or below. Life will go on. Let's say they stop at T4. They stop for T5, and then T6, they go back. T7, they go back, and T8, I don't care what's going on anymore. All right, so we'll just, in fact, we'll just erase T8 because I don't care anymore. All right, so same thing. If I want, I can do multiples. All right, it gets a little uglier, but that's okay. We can deal with that. So I've got position. I'm going to draw my position time graph. If I were to draw this, all right, I'm not going to draw it over here. I'm going to see if I can just mentally pivot this. Okay, because I'm going to twist it 90 degrees again. All right, so at T0, I'm at position 0. Check. All right. Now I've got a lot more seconds. So 1, 2, 5, 6, 7. See, I knew there was a reason why I had to get rid of T8 because I ran out of room. All right, so here we had unified spacing on the way up. So let's just say I've got a dot here, 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 and here. All right, so I'm just going to do this first part. So I start off 0, 0, and then I'm here, and then I'm here, and then I'm here. All right. Then I stood still. All right. So at time 4, I have not changed my position. At time 5, I have not changed my position. At time 6, though, all right, at time 6, now I am moving back because I basically had 3 dots here, dot, dot, dot. So I have 3 dots here, and then I have a dot here and a dot here. So I have to drag this guy out at 6, and then at 7, I am back down to here. So now if I trace this out, we can see, just by connecting the dots, we've got a much more complicated position time graph that shows the different speeds by showing different slopes, but just by drawing the dots and translating it over, I was able to see what's really going on here. All right. So we can see that during this time interval they were stopped, which lines up with what we said here, and then they sped up and all those things. So please use position time graphs as a tool along with motion maps. One can be created from the other. They're both excellent ways of seeing what's really happening and understanding it. If you have any further questions, as always, see you in class.